Hi, my name is Bryce, and this is Lab 4 Circuits. The purpose was to look at a bunch of different circuits containing different resistors in series and in parallel, and determine how the real life, our calculations matched with our predictions, or matched with our experimental model. And then we also examined how ohmic resistors and capacitors work. The first part was looking at an ammeter. I'm looking at this circuit where we had a 1.5 volt, two of those 1.5 volt batteries in a singular loop, and then we connected two ammeters just to measure the current, which had no resistance. And this was a 47 ohmic resistor, and this was a 100 ohmic resistor. And I said that the current here and here is going to be the same because there's no, they're in the same loop. And then we replaced one of the ammeters with a voltmeter, and the ammeter was 0 because now the thing's not connected. So this current is going to be different than this current because there's nothing charging right here. So it was 3, which is what these two batteries add up to. And then we went around the circuit and we put the voltmeter at different points to measure the potential difference across those. And for this point specifically, we did so B to C. It starts at 3 and it ends at 3 because there's no other loop connected and there's no resistance. So it would be the same. So the potential difference would be 0. And then the sum of all of these potential differences should add to 0. And it did because it's one loop. And this is that graph here. And then we measured the current through the ammeter in parallel with the resistor, not in series. And the current was larger than before because the current was being split between this wire and this wire. And so the current was larger because some of it wasn't actually going through here to be resisted against, I guess you could call it. And then we calculated the resistance of each using the current that we had measured and also the delta V values that we had gotten. And the resistance was slightly different for these, but it was 0 for those because that was what we assumed in the lab. And then for part 2, we investigated a resistance and capacitance circuit, and we observed how the capacitor, light bulb, and battery interact, and then specifically the relationship between how long it takes a capacitor to charge in this circuit. And then basically what happened was, as the capacitor charging current flows, and then in this case it was clockwise, and then it stops flowing when the capacitor is fully charged. And then when you take the battery off, which this was a 9-volt battery, and then we did a 10, 20, and 30 ohmic light bulb, and then we did a 200 millifarad capacitor. And so basically when you disconnect the battery, it flows in the opposite direction because now the capacitor is being discharged, and it starts out bright and then it becomes dark because now the capacitor is completely discharged and no current is flowing. And we measured how long with each of the different resistors. So this one was 10, this was about 17. And then we used this equation because it was a exponential decay of voltage over time. And we used a 30 ohmic resistor, same circuit. We charged the capacitor with the 9-volt battery completely. Then we started each second and we measured the voltage. At time 0 it was 9 volts. At time 20 it was 0.32 volts. And this was each one of the times that we measured. And notice how at first it decreases exponentially, or it's decreasing exponentially because it decreases a lot at first, and then it's going to asymptote, and then you get the voltage. We linearized it, and we got this line. And were there any discrepancies of the RC value between the experimental versus expected? The expected RC value was with resistance times the capacitance, which was a 30 ohmic resistor, 0.2 farad capacitor, so it was about 6 seconds. And then we took the slope we got from here, and we set it. We set the RC equal. We rearranged this equation. We set RC equal to -1 over the slope, so -1 over -0.1662, and we got about 6.02 seconds, which was about the same. And then what if we were doing this in real life and we had an actual ammeter? Well, the real ammeter has resistance, so it would change how much current is actually being able to flow because it's adding resistance. Still be the same. It still add up to 0 throughout the one singular loop, but also the wire has resistance, and then also in real batteries decay over time, so they wouldn't really be at 9 volts every single measurement if you use the same one. And then also, if we used a real battery to charge a real capacitor with no resistor, it would almost charge instantaneously, but remember, the wire would have resistance. However, in the model that we done online, the capacitor would charge instantaneously because there is no resistance. And then conclusions, the sources of error were assuming that we had different components, or the different components had no resistance, which they did. And then we weren't too far off because we were using a computer model. And then charging/discharging of a capacitor is an exponential function in relation to time.